lecture on Kirchhoff's voltage law and Kirchhoff's current law. In this lecture, I'll briefly look at Kirchhoff's voltage law and at Kirchhoff's current law, and I'll do an example that illustrates how you use each of those laws. Remember that Kirchhoff's voltage law and Kirchhoff's current law is nothing new. These are really just based on Ohm's law and on the conservation of charge and the conservation of energy, which you already know. Kirchhoff's voltage law states that the algebraic sum of the voltages around any loop must be zero. So the sum of the voltages supplied must be equal to the sum of the voltages absorbed. Remember that a loop is any closed path in a circuit, and we looked at that last week. So if you have any closed loop with any elements in it, then the sum of the voltages around that loop must be equal to zero. Remember that because we don't know whether voltage sources are supplying or absorbing current, for example, in the case of a battery being charged, we can't always assume that the voltages sources are supplying voltage. They could be absorbing voltage. Let's look at how Kirchhoff's voltage law works by applying it to this example. The 3-volt source and the 4 kilo ohm resistor in this example are clearly in parallel because you can see that they share this common node and they share this common node. And we know that elements in parallel have the same voltage. So we can tell over here that because the 3-volt source and the 4 kilo ohm resistor are in parallel, we know that V2 is equal to 3 volts. So we already know over here that V2 is equal to 3 volts. Now we're going to apply Kirchhoff's current law to the other loop. And we're going to go around the loop. We're going to start at a point. So we're going to start at this point, and then we're going to work our way around the loop to write down the Kirchhoff's voltage law equation. And my hint is that you should remain consistent in the direction that you are traveling around the loop as you write down the voltages, and then write down the sign that you get to first in the equation. So over here, V1 traveling in this direction, we get to the plus sign first. So we're going to write down by Kirchhoff's voltage law, we get to V1, and that's positive. And then we keep traveling around the loop, and then we get to V2, and we get to the plus sign first. So we add plus V2. And then as we keep moving around the loop, we get to the minus sign first. So we write down in our equation minus 9 volts. And the sum of all the voltages around the loop must be equal to 0 by Kirchhoff's voltage law. So all of this is equal to 0. But we know that V2 is equal to 3 volts. So we can substitute that into the equation. And then we've got V1 plus 3 volts minus 9 volts is equal to 0. So that means, therefore, that V1 is equal to 6 volts. And if we apply Kirchhoff's voltage law to the small loop, then we'll see again that Kirchhoff's voltage law also shows us that the voltages the voltage of the 4 kilo ohm resistor is the same as the voltage of the 3 volt source. So let's go around this loop starting over here, and we're going to travel around this loop in this direction. So we go along and we first get to the plus sign of the 3 volt source. So we write down plus 3 volts, and then we keep moving around the loop and we get to the minus sign first of V2. So we write down minus V2, and the sum of the voltages around the loop must be equal to 0, so that's equal to 0. And then, as we saw before, from the elements being in parallel, we can see that therefore V2 is equal to 3 volts. Kirchhoff's current law says that the algebraic sum of the currents at any node must be 0. So the currents, that means that the currents into the node must be equal to the currents out of the node. And remember that a node is a point that connects 2 or more branches in a circuit. So let's say we have a random node and we've got a number of branches connected to it, and we've got I1 flowing into the node, I2 flowing out of the node, I3 flowing out of the node, and I4 flowing into the node. Then we can either write the equation in this form, so we can just sum the currents into the node and equate that to the currents out of the node. So then we would write I1 is flowing into the node plus I4, which is also flowing into the node, is equal to I2 plus I3. The other way of doing it would be to just use the algebraic sum of the currents at a node and equate it to 0. And in that case, we have to randomly assign a sign to the currents flowing into the node and to the currents flowing out of the node. So let's say that the currents flowing into the node are denoted by a positive sign. So then we would write plus I1, and the currents flowing out of the node, we're giving a negative sign, so it's minus I2 minus I3 plus I4 is equal to 0. Let's apply Kirchhoff's current law to this example, and I've chosen an example with a dependent current source so that you can also get used to working with dependent sources in a circuit. And you can see over here in this circuit that it only has 2 nodes. So it's got an expanded node at the bottom here. This is one single expanded node, and this is one single expanded node. And so as a result, we know that in each branch, the voltage is equal to V out, because all of these elements are connected in parallel. So let's assume that we've got a current over here that's flowing in this direction, and we'll call it I2. So if we write down the Kirchhoff's current law equation for this top node over here, then by Kirchhoff's current law, we have 5 amps flowing into the node. So we've got 5 milliamps, is equal to, and flowing out of the node, we've got I1, and we've got plus I1 over 2 plus I2. And now how are we going to tackle this? Because we've got a single equation, but we've got two unknowns in this equation. So what we're going to do is we're going to write everything in terms of V out, and then we'll have one equation with one unknown. So we can write this as 5 milliamps is equal to, and we know by Ohm's law that I1 is equal to V out over 3 kilo ohms, 3,000. And now we put that into this variable here as well, and then that turns out to be V out over 3,000 times 2, and I2 is equal to V out over 6,000. And then if we multiply out by 6,000, we get 30 is equal to 2V out plus V out plus V out. So therefore 30 is equal to 4V out, and therefore V out is equal to 7.5 volts. And with this quantity we can now work out all the other quantities in this circuit. Here's another example in which we'll use Kirchhoff's current law and Kirchhoff's voltage law. So let's start off by writing Kirchhoff's current law at this node over here. So we can write by Kirchhoff's current law, we've got I1 flowing into the node, and that is equal to I2 plus I3, and they are flowing out of the node. But we know, because of this current source over here, we know that I1 is equal to 2 milliamps. So therefore we know that I2 plus I3 is equal to 2 times 10 to the minus 3. And now we've got one equation with two unknowns. But we can see that these two are connected in parallel, so therefore we know that V2 is equal to V3, and so we can write I2 as V2 over 3 kilo ohm plus, and we're going to use, instead of V3, we're going to use V2 because we know that they're equal to each other. So we can write V2 over 7 kilo ohm is equal to 2 times 10 to the minus 3. So if we multiply out, we get 7 V2 plus 3 V2 is equal to 2 times, is equal to 42. So therefore V2 is equal to 4.2 volts. Now we can use voltage law to work out the voltage across this 2 milliamp current source. So by Kirchhoff's